All right, on number 1, and most of you, I caught it as I went around to help, but on number 1, when you're doing the, when you have the nail, okay, the big deal with the nail is to make sure that it doesn't really matter where you're putting these. They'll pretty much reside on the surface of the conductor as much as they can, and they are just randomly. They don't have to be, they can be kind of shared amongst all the atoms, okay? With the other one, though, you need to make sure that you show that the negative is bound to it. And even though this isn't necessarily the shape of the atom, you want to make sure that you're kind of showing the difference between it being regular shape and then being elongated later, okay? So later you have the Van der Graaf, and the Van der Graaf definitely has positive charges as well. We're just not showing them. So on this side, when you have the insulator, I don't change anything about where the protons are. How do I draw in the electrons? Yes, so the electrons are all going to be here, and it kind of looks like they're all kind of getting squished, with the electrons trying to get as far away as they can from that negative charge, okay? However, when you do the nail over here, where are the electrons? They are as far away as possible, so they're here on the tip of the nail. Okay, so they literally move. Okay, look at the next one. The next one says, okay, so what kind of charging is it in number 3? If you all keep talking, I won't. So stop talking. Number 3, charging by conduction. Okay, so tell me what you think is happening. Electrons are going to move. Good. Now, here's the big thing. Here's how, the way you draw it is important. If this is the Van der Graaf and this is the little metal thing, by the way, why aren't the electrons going to travel through the person? This is, you've got to understand the whole situation. Why not? Insulating handle. So it's as if it's not being touched. It's by itself. It's floating in the air. Okay? So when I look at this with the negative charges everywhere, I cannot change the distribution of the protons. Where do I put the electrons now for this thing? Now this is right as it's right before it's in touch with the Van der Graaf. Okay, we have to be careful about where are they. They have, well, if it's further out, yes, but as I get really close to this Van der Graaf, they're here. They're as far away from the Van der Graaf as they can get. So now it touches the Van der Graaf. What's going to happen? What's going to move? Protons are not moving. Protons never move. What's going to move? To what? Yes. So electrons move from the Van der Graaf to the pie pan. And then when I take it away over here, I still have my positive distribution. What else do I have now? Good. Now, I have to be careful. How do those electrons now orient themselves? Because when I was close to the Van der Graaf, I had electrons here congregating as far away from the negatively charged object as they could. But now that I'm not in the presence of the Van der Graaf, what happens? They're everywhere. They space out, and I just have more of them. So the net charge, or the total charge on the pie pan is now what? Negative. Okay, so we did charging by conduction. Let's talk about the things that we've learned about conduction. So tell me what you know. It requires touching. Okay, it requires that there is an excess charge. Yes. And then what's the other thing? The object that was neutral becomes negative. Be careful. What does that mean? Negative in this case only means negative because the Van der Graaf was negative. So make it more general. Same charge as the charged object. Very good. Neutral object. Because when we do by induction, it becomes oppositely charged. Okay, so the neutral object becomes same charge as charged object. Okay, so look at number 4. So now we have our charged pie pan, and we touch it to a neutral pan. What happens? Okay, so if I bring in, so here's my charged pie pan, right? And I'm going to bring in a new neutral one. Okay, so when I do that, what first of all happens to these charges as I get close to it? Yeah, so I do the same thing happens, and now what's going to happen? I'm going to get, right, some of my electrons will transfer. Now let's be really specific this time. How many extra electrons did I have on the blue one? 4. So now when I separate them, I'm going to have the green one and I'll have the blue one. They're now separate. Okay. I still have my protons. We're going to assume these are the same size. They're identical kind of pie pans. Okay. So how do I put the electrons in there? It's going to be the same. So I'm going to have, so I would have 2 extra on either one. So basically the electrons will spread out evenly. Now if they're not the same size, it's not going to be 100%. It's not going to be just split it in half. But as long as they're identical, it's 50%. Okay. Any questions by that? Okay, by what method did the unpanned pie pan get charged? Conduction. Why is it conduction? They touched and they ended up with the same charge. Okay. All right, look at number 5 and tell me what we have going on. Induction or conduction? Okay, we have induction initially. Okay, induction initially. But what else do we have going on? There's also some conduction going on of some kind because those 2 pie pans are touching each other. Okay, so we have to be very careful about a couple of things in this one. So I'm going to give you a couple of things to think about maybe. All right, so we have our Van der Graaf with the excess negative charge. Okay, and we have our 2 pans. What happens? Let's assume they have, I'm just going to give them 4 to make it easy. Okay, where are the electrons? Yeah, the electrons, and probably not all of them, so please make sure that this is, am I showing every proton in this object? No, so I'm not showing every electron either. This is just showing an idea, okay? But I'm going to show, why am I putting 8 electrons way over there? Trying to get as far away from this as possible. Now, I know McKenna has already figured out that there's a difficulty to the next step. So I'm going to separate the pans. When do I separate them? When do I separate them, though? When you feel like it? All right, when do you feel like separating them? Right now. Okay. So we're going to separate them while we're close to the Van der Graaf, or we're going to separate them after we're far away from the Van der Graaf. So which one is it? Okay, so let's do it both ways. All right, so we're going to separate it in the presence of the Van der Graaf. If I separate it in the presence of the Van der Graaf, what is the charge going to be for the left pan? Positive, and the charge for the right pan? Negative. Okay, if I keep them touching each other and I move away from the Van der Graaf and then I separate them, what's the charge on each pan? Neutral. I would write some notes to myself. It depends. Because this is charging by induction, what do I have to have present? I have to have a charged object present. If I don't have a charged object present, am I going to change neutral objects into anything else? No, okay, I won't. All right. So let's look at 6 and 7. We're not going to finish 6 and 7 right now. We're actually going to move into something else, but I want to talk to you about them really fast. Okay? So what's happening first? Charging by induction or conduction? Induction or conduction? So what do you call, what is this part? Induction. Okay, yes. So on 6, it's induction to start with. And then what is that funny little stick figure doing? What's the whole, like, it looks like their hand grew like 4 feet. And they touched something. What are they doing? What's happening? It's grounding. What does that mean? Yeah, they touched it. Okay, so all it means is they've got this insulating handle. So the insulating handle is keeping them from touching the pie pan. So if I want to ground it, literally, I take my hand and I touch the pie pan because I'm touching the ground. I'm already grounded. So if I touch the pie pan, what does that do? Well, it does something. I'm not going to tell you what it does. What does my touching the pie pan give it access to? Electrons with the Earth. Now, those electrons in the Earth can travel up from the Earth, or they can travel down into the Earth. It totally depends on what the situation is with the charge. And I want you to do some thinking about that before we say what's going to happen. Okay? And then in number 7 is highly unlikely. I get that, but it's really fun to think about. Well, maybe not fun. Okay, so there's a lightning rod stuck through the ceiling, and it's near this guy that's hanging upside down. Okay? And you have to see what's going to happen when this lightning rod gets struck by lightning, and now we'll be holding all this extra charge. Okay? All right, look at worksheet 2. There are not many places in this curriculum where I give you an equation that we didn't get from a lab. All right, folks, pull it back together. This is not easy stuff. We're going to make an analogy between the gravitational force and the electric force. Okay, I'll wait till you're ready. I know it's hard, but we still have to get through it. Okay, gravitational force and electric force. We're going to make a comparison here. When you were dealing with the tape, you should have seen that, wait a second, even in the presence of gravity, the electric force was still significant. An electric force was able to make the tape move, even in the presence of gravity. That should tell you there's something kind of a big deal about the electric force. Okay, it seems really small, but maybe the effect is a little bigger than we think. The gravitational force, do you remember? I know you know how to do it if I wrote it this way. If I wrote Fg is equal to mg, this is what you use all the time, right? This is the gravitational force that we know is specific to the surface of the Earth. But if I want the one that is universally true for figuring out the gravitational force between any two things, what would it be?
It's the one where
Well, not mine, yes. G times M1, M2. Yes. Okay. What's the G? It's just a constant, right? Okay. What are the two M's? Okay. And what's the R? Okay. What did you figure out in lab was the determining factor for the electric force? Distance between them and what else? The charge, because we didn't have an electric force if at least one object wasn't charged. Okay. So what we're going to find out is that the electric force has a very similar form to the gravitational force. It looks like this. Okay, so now let's make the comparison. What do you think K is going to be? Some constant, okay? K is a constant. It's 9 times 10 to the 9th. And I'm going to give you the units in a minute. What's R? Distance between the two charged objects, okay? So what is Q? This is charge, right. Now, the Q is the charge. The unit is Coulomb. It's a capital C. Okay. Coulomb. Yes. Now, we're going to do a little example of a problem, solving it, just so that you get used to it. When we're dealing with charge, we're dealing with very small numbers for the most part. So we have to get used to using our calculators again with exponents and small things. So let's figure out what the unit has to be for K. What is the unit for, well, because first of all, what's the unit for electric force going to have to be? Newton. So these have to cancel out to Newton somehow, right? What's the unit here on top? I'm going to have something is K, which we don't know yet. The Q times the Q will be Coulomb squared. On the bottom, what will I have? Meter squared. So I need to make sure my distance, even though it will be really small, is in meters. Yes, very good. It would be Newton meter squared over Coulomb squared. That's my unit for K. Okay. Now, let's do an example. Here's your example. So it works the same way as the gravitational force. The further I get away from something, the smaller that force is. And it falls away pretty fast because it's r squared. Okay? So let's give you the example. So I want you to find the electric force when Q1 is negative 1.6 times 10 to the negative 19 coulombs. By the way, that is the charge on an electron. And charge 2 is positive 1.6 times 10 to the negative 19 coulombs. That's the charge on a proton. And we're going to say that their distance apart is 10 micrometers. Now, on your AP equation sheet that you really need to be using for this unit so that you're more familiar with it, on one side of it has a chart so that you don't have to remember prefixes of any kind. So you can always know what micro means or milli or whatever you're looking for. This is 10 times 10 to the negative 6. Okay. What? Nano is smaller. Okay. So find the electric force. Go ahead. Oh, and you've got your K, 9 times 10 to the 9th. Okay. Go ahead. Figure out what it is. Use your calculators. This is the time you need to figure out if you're doing something wrong with the exponents. Or you definitely don't have to have a calculator. You can do math without a calculator with exponents.
Oh, wait.
Yes.
So like the Q's are always the same?
Okay, draw the force diagram. Go ahead, on the picture. You can read it, see what's happening. There's another charged object being brought near to it. How many forces should be there on the sphere? 3. Yep. Just this one. Just this one. Okay, check this. Yes. No. Why? Which way is this pushing this? Yes. Okay, good. Okay, so did you get the force diagram? Now today, and I didn't see it wrong on anybody's that I looked at in here, the 3 forces are, which ones? What are they? Tension, Okay, and earlier today I was seeing people draw the gravitational force in the middle of the string. You're not drawing the forces on the string, you're drawing the forces on the sphere. So your gravitational force is here. Where's the electric force? To the right or to the left? To the right. Now, why is this a little harder? Okay, very good. So now this thing is in static equilibrium, which means it's not moving. But what we know about x and y direction, what do we know? They're independent, right? So if they're independent, and we know that the y components are equal to each other and the x components are. So I have to split this tension force up into two components, okay? All right, look at number 10. I'm just trying to point out some things that will help you as you're looking at this. Number 10 has 3 charges. And you are being asked, this is charge 2. This is charge 1. You can tell, I'm not going to write everything up here from your paper. Okay, this is negative, this is positive, this is negative. We want to draw the force diagram for the one in the middle. Go ahead. Draw the force diagram on the one in the middle. How many forces will you have? No, ignore gravitational force. That's a good question. 2. So you have 2. Okay, so tell me the directions of the 2 charges. Okay, but which way will charge 2 exert a force? Which way will the charge be from charge 2? Okay. We want to know the force on charge 1 from charge 2. Okay? So I'm going to label it as charge 2 just so we know. Okay? What about charge 3? How will it affect charge 1? To the right. And is it longer, shorter? Okay, now sometimes we wouldn't be able to tell. Do you understand that? Sometimes if it were a bigger charge but it were further away, we might not know. But in this case, it's a bigger charge and it's closer. So that tells me that this force from charge 3 is going to be bigger. So which direction will the net force be? To the right. Okay, here's my question. When you calculate, when you use Coulomb's law, and you do KQQ over R squared. Now remember, the 1 and the 2 just refer to the 2 different charges. They can be any 2 charges. When I calculate it between 1 and 2, I have a negative and a positive charge. So what will my answer be? Negative or positive? It'll be negative. It'll be attraction. When I calculate this one, will it be negative or positive? It will also be negative. Do you understand that the answer that I get does not tell me direction? Okay, so you have to be very careful. You have to look at your diagram to know what that means for direction. Okay, so you can disregard the sign once you're figuring that out. Okay. Well, you're going to however you want to do this, if you want to just take away all of the signs and just subtract this one from this one to find the magnitude, then you can show the direction, or you could describe the direction as being toward charge 3. Okay, so anything that you can use to describe it is fine. All right, look at the last one. Number 11 is definitely the hardest one. This is charge 3. This is charge 2. Again, you're doing the force diagram on charge 1. You're again ignoring gravity. So go ahead, draw in the forces. Yes, you have, this is a positive charge, this is a negative charge, and this is a positive charge. So draw in the forces acting on charge 1. After you draw the forces in for that, pull up your Chromebook and the calendar for the class, because I'm going to show you the link that we're going to use. All right. Tell me what you had. Which way will charge 2? What will the force look like on charge 1 from charge 2? To the left. Okay, so it will go like this. This is the force from charge 2 because it's attractive. Good. What else do I put up here? Right, it's going to be at an angle. It has to be in a straight line from that charge. So this would be the force from charge 3. So now the question is, determine the magnitude and direction of the net electrostatic force. By the way, that's why we're ignoring gravity. It's only saying electrostatic. So what do I have to do? How do I figure it out? I'm going to have to draw in some components, figure out some angles. How do I figure out angles here? You have some distances on the paper that you can use to figure out angles. Okay, so definitely the hardest one. So for homework, you should finish all of worksheet 1. You should try all of worksheet 2. If you get stuck on number 11, that's a good sign that you could do all the way up through 11, right? Okay, then pull out worksheet 3. Worksheet 3 is what we're going to do with this simulation. So pull it out. All right, when you're on the calendar, I've given you a few things to help you. Okay, so if you look on the calendar on yesterday's date, I put a whole bunch of links. So this first link is this guy who is awesome. And you can't hear it. I can hear it in my head. He does some really great demos that are super good for electrostatics. Okay, he's fantastic. And then this one for electrostatic induction is another guy who does who explains everything that we're talking about with electrostatic induction. It's a good one to watch and listen to. Okay. And this one, balloons and static electricity, is a FET. And so here, this is kind of, it's easy and simple, but it's a really easy way to kind of see what's happening. I take the balloon and I rub the balloon on the sweater. Okay, now, why is that happening? Because I pull the balloon over here, it just goes back. I pull it over here, actually something else that put. Why does it keep going back to the shirt? The shirt is now positively charged and the balloon is negatively charged. Look at that balloon. The balloon is an insulator. It's not a conductor. If the balloon were a conductor, what would all of those negative charges have done? Look at the balloon just by itself. How would the negative charges have behaved if it were a metal conductor? They would have spread out over the whole thing. What did they do instead? They stayed right where they were acquired. They did not migrate. They stayed in place. Okay, now look what happens. So this one's good for helping you with this. What happens when I go near the wall? Now I don't like their example. It's really not nice. I really like to see that they're bound to the through the nucleus so that you just see the change in shape. But can you see the induction of the charge? Okay, you can see that I'm not changing the overall charge, but I am inducing a charge. Okay, all right. So that's a good one. And then you can see, we'll go to this one. That was balloons and static electricity. This is on the calendar. Okay, this is from yesterday. John Travoltage is another one. Now, John Travoltage, this is all about, you can take his foot. Now, why are the electrons moving? He's a conductor. Okay, he's a conductor. So this is not like the balloon. And if I build up the electrons enough, he gets shocked. Okay, so there we go. And you can't hear it. I can hear it in my ear. Okay, so that's what's going on with that one. When you go back to this one, this is the one I want you to go to, is charges and fields. Okay, so if you need to see it again, it's right here, charges and fields, or you can click on today where it says FET link. Okay, this is what I want you to see. It will help us to visualize what's going on. All right, I'm going to put a positive charge up here. And I have this really strange set of arrows that show up all of a sudden. How are they pointing? Outward, away from the positive charge. I'm going to put this little sensor here, and that is indicating, it's actually indicating something called the electric field, but also the electric force. Okay, what's going on with this force? Watch what happens. Why is it doing this? Why is it getting so big and then so small? Very good. Okay, so as I get really close, if I get these two charges close together, then the force gets really, really big. And then as I take it further apart, it gets small really fast. Okay, all right, so now let's change it. I'm going to put a negative up there. Which way do all the little arrows point? Towards it. And now I'm going to put this little sensor up here. Now, I want to know the charge, the sign of the charge on the sensor. Is it positive or negative? Why do you think it's positive? Give me two pieces of evidence for why. Okay, so it's being pulled toward the negative charge. What did we notice? And now it's pointing away from the positive. Okay, so this little sensor we call a positive test charge. Okay, so it is positive. Now, this is what I really want you to see. We've got a positive charge here, and these little arrows are kind of hokey, but they show us what we call the electric field lines. Okay, if I add a negative charge, the two charges are interacting with each other, and it's forming an electric field where the two are interacting with each other. Okay, I can add as many charges as I want to kind of visualize what's happening. And look at worksheet 3, which I don't have in front of me. Okay, worksheet 3. When you look at worksheet 3, you're drawing electric field lines around different shaped objects. Okay, if I want to know what they look like, I could, for example, you see the one that's like a positive plate? I could just put a whole bunch of positive charges next to each other to kind of see what it looks like. Does that make sense? I could make it big. Now I'm going to help you with drawing them on a two-dimensional surface because it's kind of a hokey thing to use all those funny arrows. Okay, so let's show what it looks like. Now first of all, what's this idea of an electric field? Why does that sound weird? We've been dealing with the gravitational field all year long. This is the ground of the Earth. This is an object. These are some height above the Earth. Okay, so object up here. Okay. What we have going on is this. These blue lines represent the gravitational field. That gravitational field is the reason why when I put this object here, there's a force exerted on it in this direction. Does that make sense? Okay, so I have an electric field that exerts a force on an object that's present in an electric field between two charged objects or around a charged object. What does the gravitational field depend on? Mass. What does an electric field depend on? Charge. Does everybody see the difference? The difference with charge is we have positives and negatives. The difference with mass, we only have positives. Okay? All right, so now with this electric field, how does it look? You've been dealing with gravitational field all year without knowing it. An electric field, let's say I have a positive charge. The way we draw the electric field lines is out from the positive charge. If over here separate and not interacting, I have a negative charge, then to draw the electric field lines around a negative charge, I draw them all toward the negative. The reason is very simple. Somebody said so. They decided that we determine the direction of these field lines based on the direction that a positive test charge would feel the force if placed in the field. So positive charges would be attracted to negatives, but they would be repelled from positives. That's how we determine the direction. Okay. Now what happens if they interact together? So if I put the positives and negatives together, I'm trying to help you see visually how we turn those crazy arrows into actual field lines on paper. Okay, so if I have a positive and a negative here, the field lines kind of do this. And then they all point in the correct directions. By the way, that's not drawn very nicely because it's supposed to be, oops. None of the field lines ever cross each other. Okay, kind of looks like that. Okay, kind of crazy. Now, it's three-dimensional, and that's why it's hard to put it on a two-dimensional piece of paper because it's filling all the space, but this is the idea. Now, what would happen, do you think, if I have two positive charges interacting? And I'll draw it here, and then we'll go look to see what it looks like. Positive, positive. Are they attracted? No. So can you imagine that I could find a spot in the middle of these two where nothing would happen? So I could conceivably, if I had enough actual energy to actually do the work to get it there between two positively charged particles, I could actually get something to just sit right there. The force would be canceled out. Okay, so these repel each other, and this is what the field lines would look like. Any questions about that? I know there's tons of questions about that. Doesn't make any sense yet, but you will. So here, if I take all of these, if I put two, it's hard to see here what's going on because they show all these funny little arrows like that. That's why I drew it on the paper. Okay, you can't see it as well. Okay. All right, questions? You're like, I have 40,000 questions, Mrs. John. Okay, so what you have, worksheet 3, by the way, cross off number 5 completely. There's no math on worksheet 3. Worksheet 3 is 100% conceptual, just trying to figure out what these fields look like. Because gravitational field is easy. It always points down toward the Earth. Electric fields are a little different. They don't always point the same direction. Okay? So worksheet 2 is your math practice. Worksheet 1 you should be mostly finished with as it is. You've got 22 minutes before the end of class. This is not turning into a free-for-all. I understand you are totally thrashed. I get that 100%. But you still need to accomplish what you need to accomplish. And the other thing is I need your Chromebooks put back in the right order, plugged in, and all of that, so it's not crazy for me after school. So before the end of the period, make sure they go there. But use them to help you with all of this right now. Okay? Any questions? Okay, I'll walk around and answer questions as soon as I go write something down. If I were you, I'd start with the first part of worksheet 3 just to kind of get an idea of what it looks like so you can ask in class. And then go back to worksheet 1, finish it, and then get started with worksheet 2. That way you should probably get a couple of those done, and you can ask questions before you leave class.